Alright there teachers, it's Phil Wickins here, CAS Master Teacher. Welcome to another Delve In for 12 Min, a series of short online CPD sessions to give you, the class teacher, some ideas and resources to take back to the classroom and teach really exciting, dead engaging computer science lessons. Excellent, so let's get started. This session is about design. Now I'd like to thank Jane Waite, thank you Jane, my dear friend and colleague, who has been researching this concept of design within computing, and I think she has hit the nail on the head, bang on. This stuff is brilliant, okay? So Jane says that there is an approach to computing where you've got 4 levels of abstraction. Okay, we call this 4 different levels. Now this is not like a project where you have stages and you must start here and then you move down to the next stage and you do it in order. This can be accessed at any different stage, any time, and probably during the course of the activity or the project, then these levels children would be going backwards and forwards between these levels, altering this, going back to this, testing this bit out. At random or at will throughout the stage of their project. So don't think of this as it has to go in this order. Okay, now these are the 4 levels of abstraction that Jane talks about. So, stage 1, task. Now this could be given by the teacher. You could say, right then, we are going to do an animation based on our topic, Vikings for example. Or you could say, right, we've got a problem, we need to solve this. You need to create a program to make sure that this is solved efficiently and accurately. Or you could say, right, let's create a game. Here's the problem. I'd like a game which involves a spaceship or a car going around a track, and you're going to make it. You could start at a different level of abstraction, and then ask, well, what was the task? What do you think the brief was at the start of this? So you could work backwards and see what the children come up with, just to get them used to the idea of this concept of the whole design process. So, level 1, task. Level 2, design. Now this, for me, is fantastic. Since I've been implementing this into my computer science lessons, there has been so much positivity from the children. There's been a real learning curve from them, and it's really helped me as a teacher to target, teach and look at the gaps in knowledge and make sure that all the children are excited and engaged about what they're doing. So let's explore this design process a little bit more before we move on to the other 2 levels of abstraction. In literacy, you wouldn't start by saying to the children, right, write me a story about dragons, go! Well, I hope you wouldn't. What you would do is start a plan. So you might be gathering vocabulary. Let's have some adjectives, adverbs. How would we describe this? You might build a word bank. You might then say, okay, well, let's look at some other stories similar. Let's maybe look at the features. What do we need? What kind of toolkit do we need? You might start a display on it. And then you might start to think, okay, what about the layout? Are we going to have paragraphs, text boxes, pictures? Where are things going to go? Then you might start to, after all that, think about the content of each part, obviously in note form, bullet points or whatever, before the child even puts pen to paper and begins to write their story. Now, we take that for granted in topics like literacy, but what about computing? How often have we gone into a computing lesson, given the task, say, right, we're going to write a maths quiz, and then open Scratch and start writing it. Maybe we even say, well, you don't know how to do it, so this is how you do it. I'm going to show you on the board and now you can copy it in. What are the children learning? How are we really developing their sense of, well, this is what I need to do and this is how I'm going to accomplish it? So what we're talking about here is a level of design very similar to what you would do before writing a story. So let's look at some different examples. I need to stop saying the word examples. Demonstrations, models, for instance, of design. So you could have a design where it's like a storyboard. This has a very clear chronological sequence to it. So if you were doing an animation, for example, this would be a classic plan because it's a bit like a film storyboard. You've got very clear, this is where it's going, this is the direction, this is what's happening in each frame, in each shot, or from each angle, and then the children can annotate underneath what's going to happen. They could even put ideas in there of how they're going to code it, but they know very clearly after doing this exactly what their animation's going to look like. This design could be your algorithm. Now, we talked about algorithms in the first video. Make sure you have a look at that so you know what I'm talking about. This storyboard could be your algorithm or their algorithm for what they're then going to implement in their code. It fits all the criteria, it's step by step, it's instructions, it's what it's going to look like. However, not all algorithms have to be in sequence, in chronological order. Okay, there is definitely a procedure, but some algorithms could be rule-based rather than time-based. For example, or as illustrated in this next example, you could have a single screen plan where you get the children to draw what their screen will look like. This works really well if it is a game. You could have a Space Invaders type game in there or a racing car game, which wouldn't necessarily go from frame to frame or in a sequence, but things happen within that screen. And the child would annotate around this single screen and say, well, the ship will blow up if a bullet hits it. Now that doesn't happen in a particular sequence. It won't happen after a particular time. It will only happen when a bullet hits it. So this algorithm may be more rule-based, okay, where the certain conditions are met and then that particular thing will happen. So that would also be a really good way of showing design before they then go to implementing that algorithm within their code. I did a quiz with some of my children recently and I gave them a completely blank piece of paper and say, you're going to do your own design on this one. No pro forma, no storyboard. You can lay it out however you like. Now bear in mind, they were used to the concept of design. They'd done 2 already before coding, so they knew what they had to do to be able to have something that would help them later on. So I didn't just give them this cold. But as you can see, they have put their Quizmaster on there. They've put something to show what their Quizmaster will look like. They've either drawn it or written what it will look like. They have written their questions for their quiz on there. They've said which are the right questions to help them remember when they come to writing them. They've also put what will happen when you get a question right or you get a question wrong, whether there's sounds, whether there's a visual response. It's all in that plan and that design. Now, I would argue that that is a very simple algorithm ready for them to implement in code. These designs, these plans, serve a multitude of purposes. I'm just going to list some off for you now so you can hear the benefits of them. Number 1, it keeps children accountable. When they've got a plan to follow, it helps their train of thought go, well, I've done this, what do I need to do now? Oh yeah, here's the next part. When they're staring at code, so often children can't see the bigger picture of what's happening, where they're going. But this plan really will help them to keep accountable to what they need to be doing to achieve their task, achieve the solution to the task. Number 2, you do get children who are reluctant on computers, who are a little bit fearful, a little bit hesitant, don't really know what to do or how they're doing it. But writing a plan, they can get involved with that, and then they've got a severe investment into the project then. They know what they're doing, they know what their part is. Even if they don't know how to implement it in the code, they have a stake in this project. They've put their mark on it. They have developed their ideas, which then you can help them to then implement, or their partner can as well. You have to remind them to keep these plans succinct, keep them clear, keep them relevant, so that if they're working in pairs, which in some schools, if you've got one device per pair, you will often get them working in pairs. If one of them's ill, can the other one still follow the plan? Or if you give the plan to another pair, can they follow the plan? So keep it precise and clear and obvious what's going on. Another thing this does is that it allows the children to mark up their plans based on what they know how to code and what they don't know how to code. You could give them 3 different highlighters, a yellow, a green and a pink, for example, for instance, as demonstrated by. You could give them 3 different highlighters and say, right, RAG rate what you can or can't do. RAG, red, amber, green. So for instance, they might have a piece of code where it adds up the score. They don't know how to do that. They're not sure. So they might pink that bit, so that when they come to implement it, they know that that's a bit that they might need help with. Or designing the sprites in the background, they know how to do that, that will be green. This gives you the chance as a teacher to look through these plans and gather up and maybe group some children together and say, right, I need to teach this group how to add their scores up. I need to teach this group how to make sure their sprite can bounce off the edge if it gets too close. This will help you then to know exactly where your children are at, a bit of AFL, making sure that you know around the classroom who you've got and where. Another purpose the plan serves is if the children are into their project, they're coding, something doesn't quite work out, or they've improved something, they've made something better, they can go back to their plan. They can evaluate their plan, they can change their plan, and then you're sort of going between these levels of abstraction that we talked before to keep this flow of information, to keep it dynamic, to make sure that they're working efficiently, and it will help them to remember all this information that they've learned. So once the children have done their plan, they've finished their plan, it's ready, they've colour-coded on there what bits they can do, what bits they can't do, then it's time to implement that algorithm in the code. So our 3rd level of abstraction is then coding, is then programming. Okay, and that is where they will then transfer what they've got on the paper to the screen. They'll be implementing that algorithm, doing their designs, and I have to say, I have seen a massive increase in the quality of the visual aspect of their projects. They've spent a lot more time designing their backgrounds, designing their characters. They look a lot more like actual real cartoons or games rather than a hastily drawn stick figure just to get it to do what they wanted it to do. These are now well thought out games or animations because they've put the time and effort into thinking what it will look like, and they want it to look like that. If you've also got a slight gap between your girls' and boys' engagement within computing, so often having a plan can even that right out. I find that some children who like to rush on ahead in the computing side of things, if they're slowed down a little bit by producing a plan, the quality of what they end up with is a lot better. And then the ones who are reluctant to actually get to coding, if they've got a plan in front of them, they feel a lot more secure to then go and start to try things out and have a little bit of an experiment to see if they can actually do this. The 4th level of abstraction that Jane has suggested is then running the code. Okay, so then it's a case of let's look at how it works. Does it work? What do we need to debug? What do we need to alter? Can we evaluate our plans and say, well, this bit worked, this bit was great, this bit needed a little polishing up? So running the code as the last, the topmost level of abstraction within this concept. Now, I would totally agree with Jane that this is fabulous in implementing into the classroom, making sure that children get the time to plan, get the time to code, get the time to run, and then evaluate. Different ideas that you could have, you could give them a code to run, and then say, well, what did the design look like for this particular piece of code? Or what do you think the task was? Or even don't show them the code at all, run a piece just in full screen mode and say, what do you think the code would look like for this little piece of animation or this game? And you could work between the levels of abstraction like that to get them thinking how they all link together in their heads. So, hopefully this has been helpful to you. I look forward to hearing about your experience with design within the computing curriculum, within these lessons. Tell me if it's had an effect, and I will leave you now, and hopefully you'll tune into the next Delve In for 12 Min. Thank you very much. See you later.